Welcome to Elementary Real Analysis. Today we are going to explore two of the most foundational concepts in mathematics, the supremum and the infimum. If you have ever wondered how calculus deals with boundaries, limits, and continuous curves without breaking down, you are in the right place. We will build this understanding from the ground up, starting with simple analogies and moving to rigorous mathematical proofs. Let us dive in. Before we look at any equations, let us build our intuition. Imagine you are organizing a high jump competition. You can set the bar at 100 feet, and since no athlete can clear it, that height is an upper bound. But to find that true limit, you lower the bar to the tightest possible ceiling. That lowest possible ceiling is called the supremum. Conversely, think of a limbo contest. A lower bound is a bar buried underground. The infimum is the highest you can raise that floor while keeping everyone above it. Now that we understand the intuition of a tight ceiling, let us look at how mathematicians define this rigorously. This brings us to the supremum property, also known as the epsilon lemma. The formula states that u minus epsilon is strictly less than x, which is less than or equal to u. Here, u represents our supremum, the absolute lowest ceiling. The Greek letter epsilon represents a microscopic, strictly positive number. Finally, x is some element living inside our set. If u is truly the tightest ceiling, then pulling it down by even a tiny epsilon means it is no longer an upper bound, and some element x will immediately poke above it. To make this epsilon test perfectly clear, let us visualize it on a number line. On the right, you see our supremum, u, acting as the strict boundary for the set S. When we subtract epsilon, we shift that boundary slightly to the left, landing at u minus epsilon. Because we moved the ceiling down, we have now entered the territory of the set itself. The diagram shows an element x sitting comfortably between our new lowered boundary and the true supremum. This visually proves that the lowered boundary fails to contain the set. Now that we have our visual and mathematical definitions, let us see this with a concrete example. We will analyze the open interval from 0 to 1. This set contains all the decimal numbers strictly greater than 0 and strictly less than 1. To find the supremum, we first identify our upper bounds. Numbers like 2, 3, or even 50 are all valid ceilings because no number in our set can reach them. However, we want the least upper bound. Looking at our inequality, the smallest possible ceiling that still keeps all the decimals below it is exactly 1. Continuing with our open interval, we apply the exact same logic to find the floor. We need to identify the lower bounds. Any negative number, like -5, is a valid lower bound because all our decimals are positive. But we want the greatest lower bound. The highest we can build this floor without hitting the numbers in our set is 0. Therefore, we can confidently state our final answer. The supremum of the set is 1 and the infimum of the set is 0. This perfectly matches our formal definitions. This simple example we just solved leads us to an incredibly important rule in real analysis. Notice that the numbers 0 and 1 are not actually inside our open interval. They are strictly boundaries. The supremum and infimum act as the walls of a room. The walls contain the people inside, but the walls themselves are not the people. A boundary does not have to belong to the set it is bounding. This distinction is crucial because it allows us to define limits for sets that approach a value but never actually touch it. With that fundamental rule in mind, let us introduce a slightly more complex scenario that you will frequently encounter in exams. Here, we have a set generated by a specific sequence rule. The formula is x sub n equals 1 minus 1 divided by n. In this equation, x sub n represents the individual fractions that make up our set. The variable n represents any natural counting number, starting from 1, then 2, 3, and so on to infinity. As n increases, the fraction changes, generating an infinite collection of numbers that we need to bound. Let us figure out the bounds for this sequence by writing out the first few terms. We start by plugging in n equals 1, which gives us 1 minus 1, resulting in 0. Plugging in n equals 2 gives us 1 half. Plugging in n equals 3 gives us 2/3. We can clearly see a pattern. The sequence starts at 0 and only grows larger as n increases. Because 0 is the very first and lowest number in the entire collection, it serves as our tightest possible floor. Therefore, 0 is our infimum. Now we need to find the ceiling for this same sequence. Think about what happens as n becomes a massive number. The fraction 1 divided by n becomes incredibly tiny, shrinking almost to 0. This means our overall value gets closer and closer to 1. However, because we are always subtracting that tiny positive piece, the value never quite reaches 1. Every single number in this infinite set is strictly less than 1. This logical deduction proves that 1 is an upper bound for our set, setting us up for a final rigorous test. We have established that 1 is an upper bound, but to rigorously prove it is the supremum, we must use our epsilon test. We start by assuming 1 is the tightest ceiling, and then we subtract a tiny positive number, epsilon, from it. According to our golden rule, if 1 is truly the supremum, this lowered ceiling must fail. We set up our inequality. 1 minus epsilon must be strictly less than our sequence formula, 1 minus 1 divided by n. Our goal now is to see if such an integer n actually exists to satisfy this condition. Let us solve the inequality we just set up to finish our rigorous derivation. We can easily cancel the number 1 from both sides of the equation, which simplifies things greatly. Rearranging the remaining terms using basic algebra, we find that the condition holds true as long as we pick an integer n that is strictly greater than 1 divided by epsilon. Because epsilon is a microscopic fraction, 1 divided by epsilon becomes a massive number. However, the famous Archimedean property in mathematics guarantees that no matter how incredibly large a number is, we can always find a whole integer n that is bigger than it. Because this integer n always exists, an element always pops above the lowered ceiling. This completes our proof, confirming our supremum is exactly 1. So, we have proven our bounds. But you might wonder why mathematicians care so deeply about these tight ceilings and floors. The reason is that the real number system is continuous. Unlike simple integers, real numbers do not have a next or previous value. In calculus, we constantly need to find limits, maximums, and minimums of complex curves. As we saw with the open interval, a set of numbers might not actually have a strict maximum value inside it. The supremum guarantees that a perfectly tight ceiling always exists, thanks to the completeness property. We have covered a lot of ground today, so let us review our key takeaways. First, the supremum is the least upper bound, acting as the tightest possible ceiling for a set. Second, the infimum is the greatest lower bound, acting as the tightest possible floor. Remember that these boundaries are incredibly powerful because they exist even when a set lacks a strict maximum or minimum, and they do not have to belong to the set itself. Finally, the epsilon test allows us to rigorously prove these bounds. You have just taken your first major step into advanced calculus.